So, this is the last part for MHD turbulence is dynamo. Okay. So, what is dynamo? So, it is not like cycle dynamo. So, cycle dynamo you see, no. So, in fact, I opened it up. So, so you put a, so we generate electricity, but there is a magnet already. So, it is a magnet and the armature moves in the magnet and generates current, but you should generate current without any external magnetic field. So, you only have a plasma or MHD plasma and do some stirring or do something on it, but do not put any external magnetic field or no bar magnet, unlike the cycle dynamo, and generate magnetic field. So, it is possible. So, it was proposed in 1919 for the sun. Sun's magnetic field has been a puzzle or even Earth magnetic field. So, Earth has no bar magnet inside, right? I mean, it is too hot. So, any bar magnet will melt inside the sun or the Earth. So, it has been a big puzzle for long, but now most will believe it is MHD self induced. So, it is induced by on its own. And how is it induced by own? Can you I mean, you can easily, so let's figure out how it is induced on its own. So, if you look at equation for EB dot, EBK, let's put wave number. So, there is one term which is SVB, there is the mass. So, which is B to B. It turns out, as I said, remark, SVB does not get any energy from you, it is among themselves. So, two sets of people and one set of people just exchange things among themselves. So, that is not going to increase B, and always remember that there is a diffusion term. So, if you do not get anything from other source, EB will die, but there is another source which is SBU. So, U is to B, and this is the source for magnetic energy, which is the mode to mode transfer which I derived. So, from the mode to mode transfer there is a flux, and this is what leads to dynamo, which we understand at least on numerical simulations, a lot of analytical work, and this can produce magnetic field. And so, there are lots of evidences that this is the theory. And I think one of the, let me just make a remark that one of the leading which tilted the believers, or well, which tilted, I mean, so it was, well, fine, MHD will work, these are idealized equations, but there may be other things inside the Earth. But in 1995 there is a paper, there is a simulation done of the Earth magnetic field, somewhat realistic. The numbers are not same as Earth parameters. Earth has nu, eta, density and so on, but not quite same realistic parameters, but as best as possible. And they found this by Gladsmeyer and Roberts, in 1995, and they found that the magnetic field of the simulation, in spherical simulation, it switched, it flipped. Now, unfortunately, I do not have a slide here, but it is a very nice simulation where the magnetic field of the Earth in the simulation flipped, similar to what happens in the observations. So, then people said, well, I mean, this is really the model to try, and after that there is huge amount of work on planetary dynamo, solar dynamo from simulations and this kind of stuff. So, it is a huge field with lot of activity, and I will only show some, well, I am only going to show some applications based on energy transfers. Okay. So, these are the simulations done in our lab. So, in these simulations we keep a lot of kinetic energy, UK, and some seed magnetic field, very small magnetic field. So, EB could be much less than EB, you can in spectral simulation, so we can scatter it in different range of wave numbers. EB by UU is maybe 10 power minus 4, but we need a seed field. You can show that if EB is 0, it will remain 0 throughout. You need some small seed field, and that is also one of the puzzles in the universe. What caused the seed field? And for me, well, any small fluctuation is enough. So, there are so many charged particles, and small fluctuation will create that seed field. Okay. But anyway, there are debates on that as well. So, you can see that magnetic energy. So, these are this B, this red line is the magnetic energy EB. Now, there are various plots, you do not need to worry about all of them. So, EB is increasing with time, see. In fact, this is a semi-log plot. So, it grows exponentially e to the power gamma t. So, gamma is called growth rate, and then it saturates. In kinetic energy, look, this is very tiny, EB is 10 power minus 3, 10 power minus 4. So, EU does not change very much, U is approximately, it can decrease by factor 2. So, here is decreasing somewhat EU, but U is approximately same. EB only grows from nearly 0 to finite value. Some simulations show it becomes equipartition, some simulations find that they are not equipartition. Okay. Now, question is what makes it grow? Now, this has been, I mean, you want finer models, what is making it grow? It indeed is growing. These are box simulation, you can also do in spheres, you find that simulation. Now, the earlier models, I think I need to say this for completeness. So, this is a U field at large scale. Now, remember, it's 5/3 theory, people believe that at least without magnetic field it is 5/3, large scale force change 5/3. Now, one set of people said, well, energy will cascade like what Kolmogorov says. So, it will go to low wave numbers, so low small scales, high wave numbers, then it will cascade to B field, B at small scales. From here it will transfer, then there is inverse cascade to B, and this requires some helicity, which we did not discuss in my MSD discussion as well. So, helicity is A dot B, magnetic helicity, and kinetic helicity, which is not conserved for MSD, but that also plays an important role, U dot omega. And there are papers called alpha dynamo. Okay. So, this is a big thing in solar dynamo, alpha dynamo. This relates the fluctuation with the mean field. So, these used to be the models, this highly popular model called alpha dynamo model. You get my point? You need this inverse cascade. So, you need this magnetic energy at large scale. How can I get energy at large scale? So, well, this cascade of kinetic energy, small scale, this thing, then it grows backward. Now, in our lab we have done lots of simulation without helicity, okay, and we find the magnetic energy always, not only our lab, I mean everybody, if we turn off this helicity, still get the magnetic field to grow and saturate. The question is what makes it grow if the helicity is so important? By the way, I must also say that there are people who say, well, this is not required, but this helps. But the question is, if there is no helicity, what makes it grow? Now, it turns out that we can easily answer that question by energy transfers. In fact, this is what we discovered first. So, you remember this flux formulas, U less and B less. So, this was simulation done by Gaurav in the same paper which we wrote in 2001. There is a huge transfer. So, kinetic energy was forced here. So, which way will it transfer? So, there are 6 of them, no? Here, 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 here. So, there was one guy which was very, very good, very powerful, and that was this one. So, U small to U less to B less, which is large scale transfer, which nobody had talked about. So, this is a transfer which is large scale U to large scale B. So, we do not need these kind of transfers, we just need these transfers, right? I mean, and using this we can make models of galactic dynamo and estimate the time scale. So, time scale from these models we can say is L by U. L is the system size and U is the RMS, and you get reasonable numbers. I mean, I am not really deep into galactic dynamo, but you can get numbers which is 180 ton per time, which is 10 power 8 years or so on and so on. So, we can make interesting predictions by these flux arguments. Now, we computed this flux in for, I mean we done this flux many times. So, this is one paper by this is one paper by Deblicki, this is our Belgian collaboration, Deblicki et al. 2005. Okay. Now, this is a simulation for dynamo first with seed field. Now, what I would like you to, now there is another parameter called small Prandtl number, magnetic Prandtl number. Now, for the earth and the sun, magnetic Prandtl number is small and it is really small, it is 10 power minus 7 or so, and that cannot be simulated. So, best simulation we could get is 0.2, and people have done some tricks to go to 10 power minus 2, but I think that is using a lot of modeling. But you can see this u less to b less, this one. Now, this is wave number, x axis is wave number k. Now, this is at final time. U less to b less is one of the most significant transfers among B. By the way, u less to u greater, this is Kolmogorov flux, which is quite significant because kinetic energy is still dominant, right. Kinetic energy, as I said, is giving tiny bit, you know, this guy rich guy is just giving some small things to magnetic field. So, u less to u greater is still large, but u less to b less is the most significant transfer for small Prandtl number dynamos, and this is at final time, which is quite large. Okay. Now, these are details which you can look at papers, but I mean we are believers that this is a significant thing to look at for dynamo, and of course, we should look at other things like these and these, and it turns out one more point that b less to b greater, this one. So, b less to b greater is which one? This one is positive, right, all of them they come with positive sign. So, means there is no inverse cascade of b. If b large is losing all the time, then there must be somebody to give that, otherwise it can't be sustained, cannot be grown. So, this is the critical part, which is, well, there is one option is, so you see there is not much choices. So, this has to grow. I just want to emphasize my point. If this has to grow and if this is positive, then how can it grow? Impossible, no? So, one way is to something comes from the top and something comes like that. Okay. So, these are things which come, and that is not inverse cascade. So, this sign is definitely incorrect without helicity. With helicity, this sign may come as negative. The evidence is that there is a contribution from helicity which makes it this plus helicity effect that gives negative. Okay. So, these are observations one can make from fluxes. We can also look at shell to shell transfers. Now, I am talking about small Prandtl number, which is good for modeling sun and earth. So, these are the picture of shell to shell. So, u less, so this is u to b. So, u less to b less is like this, and u to u is forward, like forward is going down in Fourier space, and magnetic is also forward, but this is what is sustaining the magnetic field, and this is a critical input from fluxes. So, this flux formula are very useful for these computations. Okay. So, thank you.